In this video, we are going to learn Krebs cycle, or we call it the tricarboxylic acid cycle, or another name citric acid cycle. This is the second major stage of aerobic respiration, and it occurs in the mitochondrial matrix. It involves 8 steps, and these 8 steps can be remembered easily by using this mnemonic given here. Before we look at Krebs cycle, let's recap on link reaction. During link reaction, one molecule of pyruvate will become one molecule of acetyl-CoA after pyruvate undergoes oxidative decarboxylation. This involves oxidation as well as decarboxylation, which means the removal of carbon, and that's why it forms carbon dioxide. And pyruvate, which is a 3-carbon compound, will now become acetyl-CoA, which is only 2 carbon because of decarboxylation. Other than that, oxidation, we need an oxidizing agent, which in this case is NAD+. NAD+ will oxidize the 2-carbon compound acetate and then itself reduce to become NADH. This is what happened during link reaction, and this step, it actually occurs again during Krebs cycle. Where it is in this step 3 and 4, which we will look at it later. When we learn the 8 steps in Krebs cycle, we must first start with remembering all the products involved, and this mnemonic can help you to remember all the compounds involved. We start with O. Can I keep some succinate for myself? Oxaloacetate is a 4-carbon compound, and when this 4-carbon compound combines with the 2-carbon acetyl-CoA, it will form a 6-carbon compound called the citric, and this process is condensation. After that, citrate will become its isomer that we call the isocitrate. This process is what we call isomerization, and it involves the enzyme isomerases. And isocitrate is also a 6-carbon compound. Like I mentioned just now, oxidative decarboxylation, it also takes place at step 3 and step 4 of Krebs cycle. What happened here? Again, we will have the removal of carbon dioxide. That's why it forms a 5-carbon compound that we call alpha-ketoglutarate. And then again, it will also undergo another decarboxylation here. That's why from 5-carbon, it is now a 4-carbon compound that we call succinyl-CoA. And every time when there is decarboxylation, it must also involve oxidative, which is oxidation. So the oxidizing agent involved here is NAD+, which will then reduce to become NADH. As well as step 4, not just decarboxylation, oxidation also occurs. The oxidizing agent NAD+ will oxidize alpha-ketoglutarate. It will then reduce to become NADH. These 2 steps is exactly like that happen during link reaction, and we call this as the oxidative decarboxylation. The next step here, it involves succinyl-CoA. So some succinate, SO, so it stands for succinyl-CoA. Succinyl-CoA and then succinate. From this word here, you can see SU, SU. That's why the process involved here is also SU. which stands for substrate level phosphorylation. First, the phosphate group from succinyl-CoA will be given to GDP, and that's why it will become GTP. The form of energy that can be used in the cell is ATP. That's why from GTP, it will give away its phosphate group to ADP, and eventually we form ATP, which is the form of energy that can be used by the cell, and that's through substrate level phosphorylation. It's very easy to remember the process once you remember the compound involved. Succinyl-CoA becomes succinate, so the process substrate level phosphorylation. Besides from NAD+, we also have another oxidizing agent, which is FAD. Where will it involve FAD as an oxidizing agent? From no F, succinate become F, fumarate. It can easily remember that because it involves FAD as the oxidizing agent to oxidize succinate, and then itself reduces to become FADH2. So you can remember this by remembering fumarate F, that's why FAD, FADH2, F. And then from fumarate to malate is just involved the addition of water. And the last step here, from malate to form back oxaloacetate, ox, it means that here it involves the process oxidation. You guess the process based on the name of the compound. Malate becomes oxaloacetate ox, so it involves the process oxidation. And over here we don't have any alphabet F. That's why the oxidizing agent here is simply NAD+. NAD+ will act as oxidizing agent to oxidize malate, and then itself will reduce, become NADH. And that's it. We form back the oxaloacetate 4-carbon compound, which can then receive the acetyl-CoA to form citrate, and this Krebs cycle will go again. So from this one turn of Krebs cycle, I get 1, 2, 3 molecule of NADH, and then I get 1 molecule of FADH2, as well as from step 3 and 4 I get 2 molecules of carbon dioxide, as well as this step here I get 1 molecule of ATP. This is from one turn of the Krebs cycle, which involves 1 molecule of acetyl-CoA. But if you remember that 1 glucose will give us 2 pyruvate, and from this 2 pyruvate, after link reaction, it will form 2 molecules of acetyl-CoA, which means I will have 2 turns of the Krebs cycle, and all this it needs to times 2. During Krebs cycle, from 1 glucose molecule, I will get 2 ATP, 6 NADH, 2 FADH2, and 4 carbon dioxide. And these 2 ATP, they are formed through substrate level phosphorylation. At the end of Krebs cycle, 1 molecule of glucose is completely oxidized to become carbon dioxide. But so far, we only get 4 ATP through substrate level phosphorylation. We still have many energy stored within NADH as well as FADH2 in the form of electron. How are we going to extract this high energy electron inside NADH and FADH2 in order to make ATP? This is through the last stage of aerobic respiration, which is oxidative phosphorylation.